All right, we're going to start our next chapter, which is chapter 7 on kinetic energy and work. All right, so most importantly, let's start with what energy is. We've heard this term used a lot, and it's actually a little hard to define. We're going to try to define it very broadly at first. So we're going to say that energy is going to be a scalar quantity. All right, so it's not a vector, it doesn't have direction. It's going to be a scalar quantity, which basically means it's just some number associated with the state or the condition of one or more moving objects. All right, so it could be the energy of an object, or it could be energy of a system of objects you can be referring to. Some characteristics of energy. Energy can be transformed from one type to another, and we're going to look at what some of these types of energy are. And it can be transferred from one object to another. So it can be transformed or transferred between objects. Most importantly, the total amount of energy is always going to be the same. So energy is conserved. So before an interaction, whatever the total amount of energy is, it's going to equal the total amount of energy after some kind of interaction. All right, and again, we're going to look at that a little bit closer as we go forward. All right, so we're going to start with kinetic energy. Now, kinetic energy, we're going to use capital K. So this is capital K for kinetic energy. It's associated with the state of motion of an object. So most importantly, kinetic energy is referring to an object that is in motion. An object that's at rest doesn't have any kinetic energy. All right, so the faster the object moves, the greater its kinetic energy. For an object of mass m, whose speed is v, where speed is v is well below the speed of light. So we're talking about, basically what we've been talking about in class. We're not talking about anything close to the speed of light, which would be relativistic, not getting into that in this course. So our kinetic energy's relationship is going to be 1/2 mv squared, where m is going to be the mass of the object and v is the velocity. The SI unit for kinetic energy and for any other type of energy, so all energy, is going to have the unit of joule, kind of pronounced like this almost, kind of joule. We're going to use capital J, and 1 joule is going to be 1 kilogram meter squared over second squared. And you can see that from the equation, right? Because you have, in our equation for energy, we have the mass, which would be in kilograms, and then the velocity squared. So that's meter squared divided by second squared. All right, so that's going to be our unit for energy. We'll just usually refer to it as a joule. All right, so let's do an example problem. In 1896, in Waco, Texas, William Crush parked 2 locomotives at opposite ends of a 6.4-kilometer-long track, fired them up, tied their throttles open, and then allowed them to crash head-on at full speed in front of 30,000 spectators. Now, hundreds of the spectators were hurt by flying debris, several of them were killed. Assuming each locomotive weighed 1.2 times 10 to the 6 newtons. So this is a force, right? This is a weight, not a mass. They're giving it to us in a term of newtons. And its acceleration was a constant 0.26 meters a second squared. So what was the total kinetic energy of the 2 locomotives just before the collision? All right, so this is a bit of a multi-step problem. We need to kind of break it down and look at it. So let's first start by figuring out what the acceleration, or excuse me, what the speed was right before they collided. Because, well, again, with our equation, right, kinetic energy is 1/2 mv squared. We need to know what the velocity is to find out the kinetic energy. All right, so we know the acceleration. To find the velocity, we can just use our kinematic equation. So going back to our previous chapter, the one that's going to be useful is going to be this. So it's vf squared is equal to v naught squared plus 2a times delta x. And just a reminder, delta x is just final minus initial. So that's our change in displacement. Delta x is going to be our change in displacement. Okay. Well, we know that the initial velocity is 0 because the trains are starting from rest. So initial velocity is just going to be 0 meters a second. And we also know that our delta x, which is again a change in distance, is going to be 1/2 of the length of the course because the track is 6.4 kilometers long. They're going to collide at the middle if they're accelerating at the same rate. All right, so we can go ahead and say that so that our change in x is just going to be 3.2 times 10 to the third meters, changing it to meters. Again, that's just half the length of the track. All right, and so now we can go and plug everything in because we know everything that's in the equation. All right, so we have Vf squared is equal to 0 because the initial velocity was 0. Again, going back to this equation. 2 times the acceleration, which is given as 0.26 meters a second squared, multiplied by our change in x, which is 3.2 times 10 to the third meters. Okay, so solving for our final velocity, we see that our final velocity is equal to about 40.8 meters a second, which is pretty quick. It's about roughly 150 kilometers an hour. Okay. Well, next thing, I want to find the mass because, again, going back to our equation, we need to know the mass, not the force due to gravity. So let's go ahead and find that out. So the mass is just going to be, the weight divided by 9.8, right? So this is just going to be 1.2 times 10 to the 6 newtons divided by 9.8 meters a second squared. And I just got that from F is equal to ma, rearranging and solving for m. Okay, so we see that our mass is then 1.22 times 10 to the 5th kilograms. Okay, well, now I can just solve for what the kinetic energy is. So kinetic energy, again, of both locomotives, right? So both locomotives means we need to multiply the energy by 2. Okay, so we have 2 times, oops, put that back. We have 2 times 1/2 mv squared. Should make a point here that we know that velocity is a vector and they're going towards each other. So you might think that, well, one's going left, one's going right, I should subtract them. Not in this case. Notice the velocity is squared, right? So since the velocity is squared, it doesn't matter that they're going in opposite direction in this case. So their energies are actually going to add together. Okay, so that's why I have it multiplied by 2. Then if I go ahead and plug everything in for this, it's just 1.22 times 10 to the 5th kilograms times our velocity squared, which is 40.8 meters a second squared, which means our kinetic energy is about 2.0 times 10 to the 8th joules. All right, which is quite a large explosion. There's a lot of energy, obviously, when you have 2 locomotives coming at each other, and that's why it was basically like a bomb going off when they hit. Okay. So next topic is going to be work. So work we're going to use as a capital W. It's going to be our variable. It's energy transferred to or from an object by means of a force acting on the object. All right, so by using a force, you're using a force applied to an object, and that's either transferring energy to the object or taking energy away from that object. All right, so energy transferred to the object is going to be positive. Energy transferred away from the object is going to be negative. Again, so to the object is positive, and transferred from the object is going to be negative work. Okay. All right, so to calculate work, the work of a force F doesn't an object. As the object moves through some displacement, we use only the force component along the object's displacement. The force component perpendicular to the displacement direction does not do any work. So, for instance, if I had this little bead traveling along a wire, All right, so it's confined to just moving along this wire. If I apply force up and to the right, let's say I'm pulling up and to the right, the only part of that force that's going to be doing any work is the part that's going along the displacement. So this is going to be the component of the force that we need. This perpendicular component isn't going to do any work because it's not moving up or down. All right, so it's just this x component here that's along the displacement of the object. All right, so for a constant force F, the work done W is going to be given by this equation. So our work equation is work is equal to F dot D. And just a reminder, back to what the dot product is, it's going to be FD cosine of phi or theta, whichever one you want to use for the angle, right? Where this is the angle, right? And this gives us the x component of that, it gives us the x component of the force. Okay. So when two or more forces act on an object, the net work done on the object is the sum of the works done by the individual forces. So for instance, our net force is just going to be work 1 plus work 2 plus work 3, etc., 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 all the way up to work n. So it's however many forces are acting on the object, you're going to take the work contribution from each of those forces and add them together. Now they can be negative because they can work against each other. All right, so we need to keep that in mind as well. All right. The work-kinetic energy theorem. The theorem says that the change in kinetic energy of a particle is the net work done on the particle. All right, so in words, it's the change in kinetic energy of a particle is equal to net work, or our change in kinetic energy is equal to our net work. Right? And again, this delta is just the change in, which means final minus initial. So our final kinetic energy minus our initial kinetic energy is equal to the total amount of work done. Right, it holds for both positive and negative work. If the net work done on a particle is positive, then the particle's kinetic energy increases. Right, so if you're doing work and you're increasing its kinetic energy, you're going to, or excuse me, if the work done is positive, then it's going to increase the kinetic energy by an amount of the work. And then the converse is also true. So if you decrease, if the net work is negative, then you're going to decrease the amount of energy in an object. All right, so let's do an example. All right, so the figure shows that two industrial spies sliding an initially stationary 225 kilogram floor safe, a displacement d of magnitude 8.5 meters, straight toward the truck. So that's to the right. The push F1 on SPY 001 is 12 newtons. All right, so if we look at a free body diagram, going back to free body diagrams, we need to remember that she's actually pushing down on it. So the arrow is going to start in the middle and go down and to the right. And that's at an angle of 30 degrees down from the horizontal. Then the pull of F2 of SPY 002 is 10 newtons. So he's pulling up and to the right. So she's going down to the right. He's pulling up and to the right. So he is pulling like this. And that's at an angle of 40 degrees. The magnitudes and directions of these forces do not change as the safe moves, and the safe makes frictionless contact with the floor. All right, so we don't have to worry about friction going in the opposite direction. All right, the other things we have in the free body diagram, again, are the force of gravity pulling down and our normal force pulling up. So the first question is, what is the net work done on the safe by the forces F1 and F2 during the displacement? So we first want to see what each contribution to work is. All right, so for SPY 1, we'll do first. So our work 1 is going to be just our force 1 times the distance, and that's going to be cosine, I'm going to call that theta 1, right? Which is going to be 30 degrees. Right, so this is equal to the force, which is 12 newtons, times the distance, which is 8.50 meters, times the cosine of 30 degrees. Right, because we want the component that's going along that axis. Right, this means that our work 1 is going to be, it's going to be 88.33 joules. All right, now I find the work done by the second SPI. So work 2 is going to be the similar, F2 times the same distance, cosine of theta 2. So that's 10 newtons times the same distance, 8.5 meters, times the cosine of 40 degrees. Okay. That gets us a value of 65.11 joules. Now I want to add these together because it's going to be the total work done. They're in the same direction, so we can add them without having to worry about the negative signs. So our net work is just going to be work 1 plus work 2, which is equal to 88.33 joules plus 65.11 joules. So our net work is about 153 joules. Okay, so it's positive, which means that since we're doing positive work, we're going to be increasing the energy of the object, increasing the energy. Okay, the next question, during the displacement, what is the work WG done on the safe by the gravitational force FG, and what is the work WN done by the safe by the normal, or done on the safe by the normal force FN from the floor? All right, well, let's look at these. Well, if we do WG, it's going to be, well, it's FD, so it's FD cosine theta. And we know that the weight pulling down, force due to gravity, is just going to be mg. Right? So this is just mg times d. Cosine, and this is going to be the angle between the displacement and the force. All right, so if the displacement is this way and the force is this way, the angle is going to be 90 degrees, that angle right there. So this is just going to be cosine 90. Cosine 90 is 0. Right? So that means our work due to gravity is 0 joules. Right? And we would expect that, right? Because the force of gravity isn't doing anything to help push the safe across the floor, right? So the work done is just going to be 0. All right, and then with the normal force, we'll look at it as well. All right, this is going to be the normal force times the distance times cosine of theta, and again, the angle is 90 degrees, right? Because normal force is going up, the displacement is to the right, so the angle between those two vectors is 90. All right, and that's going to be 0. So the work done due to the normal force is also 0, and again, we would have expected that. Okay, so the last part is the safe is initially stationary. What is the speed, Vf, at the end of the 8.5 meter displacement? All right, so we can use the work energy theorem, which is work is equal to the change in kinetic energy. And we know, so change in kinetic energy is our final minus our initial. Oops. All right, so writing that out, we have 1/2 m, our velocity final squared, minus 1/2 mv naught for our initial velocity squared. Okay. Now we know that the initial velocity is just 0 because it's starting at rest. All right, so this whole term goes to 0. And all we're really left with is work is equal to 1/2 mvf squared. All right, so I just take that and I solve for final velocity. And so the final velocity is going to be the square root of 2 times the work divided by the mass. That's just taking that equation and rearranging it. Plugging in what I know, it's going to be 2 times our work, which we found to be 153 joules, divided by 225 kilograms, which is what was given in the problem. Square root that. All right, so our final velocity is 1.17 meters a second. Okay. Let's do another example. During a storm, a crate is sliding across a slick, oily parking lot through a displacement d is equal to -3 in the I direction, negative 3 meters, while a steady wind pushes against the crate with a force of, you have 2 newtons in the I direction and negative 6 newtons in the J direction. All right, so we're going to be looking at unit vector notation for this example. And we're going to have to remember how to deal with unit vector notation, and especially in a dot product sense. All right, so we'll get to that in a sec. How much work does this force do on the crate during the displacement? All right, so one thing to notice here is the displacement is to the left, and our force is down and to the right. Okay, and it's on a surface. So really, when I look at this force, I just want to know what component is in the x direction. What is that component there? Okay, and that's actually given, right? Because they give us everything in unit vector notation. So the component is just going to be 2 newtons in the x direction. All right, so what does this look like when we actually write it out? So let's use our work equation. Work is equal to F dot product with D. Remember, it's FD cosine theta. But when you're using unit vector notation, you don't need to worry about the angles. You keep everything in the unit vectors and in the dot product. All right, so writing this out, you have our force, which is 2.0 newtons in the I direction, plus negative 6.0 newtons in the J direction. That's actually in the negative J direction, right? And this is dotted with negative 3.0. Oops, this is in meters, because this is our distance, so that's in meters. And this is in the I direction, right, which is the x direction. Okay. So if I was just doing multiplication here, all right, lose all of the different variables and everything, but just multiplication, you have one value multiplied by a sum of 2 values, right? So you're going to distribute this to each value. You distribute this term to this and to this. All right, when you do that, that looks like this. So your work is 2.0 newtons times negative 3.0 meters, and then you're going to have I times I, because those are there too, right? So I dotted with I. Then you add negative 6.0 newtons times negative 3 meters. And then for this term, you have I dot j. I dot j. All right, well, I dot j is going to be 0, right? Because it's, if you think about what a dot product is, it's the 2 vectors times the cosine of theta. Well, the theta, or the angle between I and j, or the x and the y direction, is 90 degrees, so cosine 90 is 0. All right, so this term always goes away. So when you're doing a dot product, the only terms that actually ever stay are I dot I, j dot j, and k dot k. All right, so in this case, all we're really worried about is this I dot I. And I dot I is 1, right? Because their unit vectors don't need to worry about a value there. Okay, so the work is simply negative 6.0 joules plus 0. So you get negative 6.0 joules as your final answer for work. All right, so let me just look at the bottom left here. So thus, the force does a negative 6.0 joule of work to the crate, transferring 6 joules of energy from the kinetic energy of the crate, which means you're reducing the amount of kinetic energy that the crate has, right? So think about it. The crate's moving to the left, right? It's moving to the left, but it's getting pushed down and to the right while that's happening. All right, so you're actually going to slow it down as it's moving to the left. All right, so you have a decrease in kinetic energy, which is a negative work. Okay. The last part here is, now if the crate has a kinetic energy of 10 joules at the beginning, so if it's starting with some amount of kinetic energy, which it was, right, because it was moving to the left, or that's where the displacement was, what is the kinetic energy at the end, right? So again, work is just the change in kinetic energy. Oops, so that's kf minus ki. Oops. I want to solve for what the final kinetic energy was. I want to know what it ended with. So if I just rearrange this equation, so kf is equal to our initial plus our work, which means that it's 10 joules, because that's what's given as the initial amount of energy, plus a negative 6 joules, because that's the work. You end up with 4.0 joules of kinetic energy afterwards, right? Which means that we decreased the amount of kinetic energy. We kind of slowed the object down, moving in the left direction. All right, that's it for this lecture. We'll pick it up next time.